Hello everyone. Welcome to Devon Education Hub. Learn, build, and innovate. Let's get started.
Nature delivers electrical power with violent, chaotic precision. A single strike can heat the surrounding air to temperatures 5 times hotter than the surface of the sun. The modern world depends on domesticating this force. We run entire civilizations on a subatomic phenomenon that remains invisible to the naked eye. To find the source of this power, we have to look past the city grids and the silicon processors, plunging down into the subatomic void. Down here, matter possesses a built-in physical property called electric charge. Like mass, it is a mathematical constant that dictates how particles interact. Early researchers, like Robert Millikan, proved that this charge is quantized. Through his oil drop experiment, he showed that electricity is not a continuous fluid, but is composed of specific, indivisible minimum units, the electrons. Every street lamp, server farm, and hospital monitor on Earth relies on the precise, predictable behavior of these unimaginably small units of charge. This behavior follows Coulomb's law. At this scale, opposite charges snap together, while identical charges aggressively repel one another. These charges interact without physical contact by projecting electric field lines into the space around them, exerting tension across the vacuum. This diagram maps these invisible forces. Measuring electric flux, the density of field lines in an area, calculates the strength of isolated charges, like the microcoulomb point seen here. When multiple charges overlap in this shaded region, Gaussian boundaries determine the net force. While these stationary charges create immense latent tension, this static energy performs no work until it is forced to move. A massive concrete dam holds back a reservoir, creating immense physical pressure through the sheer weight of the water. In a circuit, electric potential, or voltage, acts as that pressure. It is the force that breaks electrons out of their static bonds and drives them forward. Inside a copper wire, free electrons bounce randomly in constant chaotic motion without a net flow. Applying voltage forces this chaos into order. They align and move with a net speed known as drift velocity, creating a structured electric current. Without a constraint, this flow would result in a destructive short circuit. Electrical resistance provides the necessary bottleneck, allowing us to convert that movement into heat or light. George Simon Ohm formalized the math behind this balance. Ohm's law dictates that current is directly proportional to voltage and inversely proportional to the resistance of the path. This equation gave humanity the exact mathematical blueprint needed to turn chaotic subatomic movement into controlled mechanical work. Modern technologies, like a camera flash or an electric vehicle's acceleration system, require a massive burst of energy faster than standard batteries can provide. Engineers solve this by using a capacitor, which functions as a pressurized electrical storage tank. By placing 2 conductive plates parallel to one another, a circuit hoards a massive imbalance of electrons, building extreme electrostatic tension between the plates. When the circuit completes, the capacitor discharges this stored energy instantaneously, releasing the hoarded electrons in a single high-power arc. These devices act as the short-term memory of the electrical world, bridging the gap between steady currents and sudden extreme demands. In laboratory theory, systems are perfectly efficient. In the physical world, every interaction involves a loss of energy. A battery at rest holds an idealized maximum energy rating, known as its electromotive force, or EMF. The moment a current begins to flow, the energy delivered to the device, the terminal voltage, drops below that maximum. Internal resistance within the battery itself converts a fraction of that voltage directly into waste heat. This internal toll ensures that the energy delivered is always less than the energy stored. Mastery of these inevitable losses is what allows engineers to build functional, reliable power systems. As circuits grew from simple loops into complex urban networks, new laws were required to track energy. Gustav Kirchhoff provided the framework for calculating how current branches and voltage drops across a vast grid. These early brass and black resistance boxes were the first tools used to manually measure and regulate the invisible forces governing our cities. Modern hardware, like these satellite solar arrays, applies these same principles in the vacuum of space. Here, engineers must carefully manage the flow of electrons from solar radiation while accounting for extreme temperature shifts. These same laws of charge and resistance extend to the stars. Much of the observable universe is composed of plasma, ionized gas where vast electromagnetic fields dictate the formation of nebulae and the radiation emitted by entire galaxies. The mechanics governing a single electron inside a battery are the same forces shaping the cosmic clouds of the deep universe. Understanding the movement of charge is quite literally understanding the heartbeat of civilization and the laws of the cosmos. To continue exploring the physics of our world, subscribe.
Thanks for watching. If you enjoyed this video, please like, share and subscribe. Stay connected with Devon Education Hub.